Morning, everyone. Hope you had a good sleep, and everyone is awake now. Today I'm going to talk about evaluation and calibration of tree growth simulations via linked Gaussian processes, which you introduced yesterday already. And similar to you, I'm going to try to avoid all the mathematical formulas and equations. It's more of a storytelling today, so like ease you in the day, a long day. So in woodland creation project in the UK, we usually use something called land carbon code. It's widely used for biomass lookup, and it provides estimates of carbon sequestration from empirical models in 5-year periods of standard age for UK tree species. However, if you're satisfied with whatever we're using already, we wouldn't be here doing research and having this meeting. So before I keep going, another concept to introduce before everyone got confused. So there's something called yield classes. It's a way of categorizing the potential productivity of tree species on a particular site. So for example, a yield class of 12, stick spruce, means that under optimal conditions, the species will grow 12 cubic meters of timber per hectare per year. And yes, like somehow yield classes goes up by 2, so it's like 14, 12, 20. Yeah, don't wonder if there's no like 13 or 15 there. Like it's not, they're just not there. And we have a quick look of how WCC curves look like. We have different species and they move pretty nice, like smooth and nice, but we will see what the problems later. Like sometimes it's too nice. Yeah, so we have WCC, then we think, oh, we've been using Jules a lot. And Jules is a process-based land surface model, which can simulate carbon cycle in natural vegetation and soils. And it's generally considered more comprehensive in the representation of multiple dimensions a user would consider. So like we think, okay, Jules may be something more similar to the reality, even though it's still a simulation, but better than WCC curves. And so our mission is, for the first part of this talk, is to calibrate Jules to WCC. So basically, what we want is we want to calibrate Jules based on the yield classes and direct growth curves from WCC, which means we want to find Jules parameters for each species that can function as WCC, which means we want one set of Jules parameter for one per species across all the yield classes that can function as WCC. And of course, when species change, the parameter set would change. But like for one species, there's only one set of parameter we're looking for. And not surprisingly, we're choosing stick spruce, same as Suzanne yesterday. And we first have a look of how yield classes across the UK look like for stick spruce. We know it's correct because from here where we are, it looks quite high. And if you look around, there are a lot of like well-grown trees here. So, sorry. Yeah, this is how WCC, yield classes look like for stick spruce. And people wonder, okay, we have Jules, we have WCC, then why do we need emulators in between? So the reason is we have selected 8 parameters in the initial stage for Jules, and it's an 8-dimensional space to search for one parameter set. It's a very huge space, and it's going to require a lot of Jules runs to go through all the possibilities and search for the one parameter set we're looking for. In this case, people who have used Jules before knows how slow it can be and long the queue is and everything. It's never going to finish running at the time you want it. So we will build emulators for Jules that we don't have to run Jules all the time. It saves time and carbon energy. So how do we calibrate it? There are 2 steps. The first step is history matching, which help us to narrow down the parameter space. And the second step is MCMC, which we're not going to cover a lot today. But that's going to help us to find the specific parameter we're looking for. So for history matching, there's one important concept, which I believe Alex will cover later as well, the implausibility, which basically means the distance between data and model, which means like the WCC curve and Jules simulation. So if it's a small value, then we consider we cannot rule out that parameter yet. And if it's a big value, we know we can rule out that parameter from the space. So there's not yet ruled out space that's in the history matching. And a simple version, very simple version of history matching is we first sample initial space filling parameter sets and run Jules. And then we build Jules emulator based on these Jules runs. And then we run these emulators over the parameter space because its emulator already is very fast. We can go over a larger part of the parameter space and to rule out the implausible parameters to create a n-roid space. And then we can keep sampling from the n-roid space, which we consider more possible for the parameter, and then run Jules again, and update or emulate and update the space until it's like stable and in a very small region. Okay, so let's not make things too complicated in the beginning. So we start with a single yield class 18. The thick black line here is WCC curve for yield class 18, and the others it's maybe because it's monthly, so I didn't integrate them so that it's like more different. But looking at it, we can see some problems. First of all, the WCC curve seems like to be keep growing all the time, while Jules after 70, 80 years is like can even go down a little bit, which is surprising, but it happens. And we can also see like in the beginning phase, most Jules runs start off going faster, while WCC curve have a long flat phase to start, and it's maybe a problem we will see later. So the first wave of Jules runs with 50 initial parameters we selected. So each line is a parameter we selected. We can see that it is indeed like the ones that match the beginning phase of now like the red curve is WCC curve. So the ones match the WCC curve in the beginning doesn't really go up to the level of WCC. However, the ones that in the end match the WCC level have a very different initial phase of values. So we now sense this may be a problem already. When we build the emulator, because we're just using parameters, parameters for Jules, we're not really, say, using like time, say the year to year parameters are the same. So we're not gonna make all these like up and downs in the curve, but like we're trying to make sure the whole shape match the Jules runs from the emulator, and we can see it's pretty much doing a good job here. At least a job that's good enough for us to run the algorithm. And this is the n-roid space after the first wave. We can see we're already ruling out a lot of spaces and focus. So this is only one, like two variables. So like there are 8 variables, but like we can already see like we're ruling out spaces that we think is not that possible. So the past week 1 result, we can see. Sorry, forgot to mention. So because this problem of we're either matching, we feel like you're either matching the beginning phase or the end values. We discussed a little bit with the Jules team, and we think, okay, maybe it's more important for now in the beginning, like the first try, to match the end values first, because that's in the long run of the calculation more important. So in the history matching, we're more focused on the differences of Jules emulation and WCC curve on the end values rather than the whole curve. So we're trying to match the end. We can see after the first wave, it's okay. Like the end value matched and the whole curve, it's okay. But still, the beginning phase still a problem, and we can see it start to die down. So even if the end value matched, we can imagine the WCC curve still growing, because it's 200 years curve. This is only 100 years, so like it's definitely gonna not we showed before, like it's not going down. It's going flat, but not down. So, but Jules, which is more similar to reality, we can see it happens like most of them start, especially for sticker screws, like it start to go down after like 60, 70 years. And we did more Jules runs within the Unreal space, and then updated the emulators, and we can see we are indeed like matching better. So the emulators are getting better as well. And we can see that the second wave running results of Jules is already like on average leveled up to more similar to the WCC level compared to the first wave. Like the first wave, like in general, are more of the lower level there, while the second wave like already leveled up. So like we know that the algorithm is like searching for parameter values that make Jules runs like more similar to the WCC curve, especially because we're focused on the end now. But yeah, so we know it's working, but it seems like we cannot get both ends. Like we can either match the end part or the beginning part. So we did a experiment with like across all the yield classes, because that's what we want, like for one parameter across all different classes. And this time we focused on the first 40 years and then plot the predictions of the last 60 years. So we can see, this time the smooth lines are the highest and lowest yield curve WCC curves. I mean, they are. So when we try to match, and this time we include all the phase. So like we're trying to do the beginning as well. Then when the beginning matched or the shape we can catch, we can definitely see for the low yield class curve, which has an even longer flat phase, it's almost impossible for Jules to catch that phenomenon. And indeed, we actually plot a lot of yield class 6 Jules against the WCC curve, which is the black one here. We can none of them actually has the beginning phase for that long, and this brings the question, like, what can we do? Because eventually, and especially for our projects, which focus like 2060, 2050, the first several decades matter. Like we want them to match to give a good calculation. So one possible solution is, although we thought we already picked the 8 most important parameters, we may have to include more parameters in Jules runs to hopefully that's going to give us a bigger variation of the curve shapes. We haven't finished doing that yet, but like fingers crossed, that's going to bring us more shapes, and then can get us both correct at the end value and the beginning shape as well. Yeah, so imagine we have found that one set of parameters that we can use to across the UK for one species and across all the yield classes. We use Jules because it gives us more possibilities. It has not only the vegetable carbon storage calculated, it also has the soil carbon storage calculated, and the corpse as well, as introduced yesterday already. So it has many, many more features. So we're thinking about, okay, can we do more than just vegetation carbons? And so this is how carbon in vegetation looks like for Jules. And for people who listened to me talking before, we have shown that the emulator at monthly level, so the linked emulator here essentially means we're building a specific emulator for each month to month step. So like January to February is the emulator, and then February to March is emulator. So it's 12 emulators of different structures keep linked and then evolving, and then we can see it's performing good enough for the carbon storage in vegetation. However, if we want to do soil as well, which this graph kind of scares me. Because if you look at this one, we can see that it has a spike in the beginning, which then it explained to me yesterday already. So like in the beginning phase, like the soil can, if you like stir them and everything, like the more carbon are stored there in the beginning. And we can see for low values, they are pretty much like the vegetation one that has a very regular seasonality and regular shape across all. However, if we go up, especially if we can look at this up one, the kind of outlines, it doesn't really show very regular seasonality, and it's like, so it means like the month-to-month structure is different all the time. And so like when the carbon storage is like high, the shape goes random-ish. Like we're not very confident looking at that graph to build a simple version of emulator to just make it work. And indeed, we tried very fast. It's nothing finished work. It's just very initial exploration, but we can see we can get the level right ish. But then the seasonality is not there. This specific curve doesn't have a spike in the beginning, but like it starts to vary like already in the beginning very much. So like, but it's because for soil emulation we don't have month-to-month soil data. So like it's same set of soil parameters across all the time. Then you kind of wonder how do I get the like variations month to month, and that's why we think about modeling soil and vegetation carbon together. So we're no longer a toy example here of like linking different months for the linked DGP. So we're trying hard. So we're thinking about can we have a more sophisticated link structure that will help us model this like soil and veggie carbon storage, because we can think they have some interactions like the classical example told by Danny, like leaves fall down from the trees and then go to the soil. So like there's carbon interactions in between. And we're thinking, can we also like we do have month-to-month differences in the input data for veg carbon. So we're thinking, okay, can these things maybe introduce to the soil carbon as well? So we're thinking about, say, once we for timestamp t, once we have the veg carbon emulator views, it can feed into the soil carbon as a value, and then also predict also fit into the prediction of the next timestamp veg carbon as well. And for each timestamp of all the emulators, we're trying to add both climate and soil related variables as input values. We're still not sure should we link the soil emulation output to the vegetable to the veg carbon one. It seems to be dodgy. Like we were still thinking about it. Maybe we'll have some experiments as well. But yeah, so we are hoping that by linking things together in a more sophisticated way, and then like say passing through information through different emulators of different carbon storage types, hopefully we can do better on carbon soil, because soil carbon, because looking at this graph with very limited input data variation, it seems like a very hard job to just emulate all these variation in soil carbon storage. So that's actually why linked GP can be useful as well. We're hoping, fingers crossed, like it's gonna give us some good results after linking all these things together. Actually, I'm done. Thank you guys very much, and